Hello friends, in this video we will discuss about transformer action using Faraday's law.
According to the Faraday's law, if there is a coil placed in a magnetic field which is varying with respect to time, in that coil an EMF is induced that is given by d by dt of n times phi. That is rate of change of n times phi, where n is the number of turns of the coil and phi is the flux. And n phi is typically known as flux linkage. So let us take this example. In this example, we have a core where we have two coils, coil number 1 and coil number 2. And the input to the coil number 1 is a voltage source, and this voltage source produces some current in coil 1. Because of this current, there is a magnetic field produced phi. And let us say now this voltage V, that is changing with respect to time. This means current will also change with respect to time and flux will also change with respect to time. And because of this changing flux, we will have an EMF induced in coil 1 as well as in coil 2. So let's say the number of turns in coil 1 is N1 and the number of turns in coil 2 is N2. Then the EMF induced because of this flux phi in coil 1, E1, is nothing but N1 phi. But N1 is a constant, so we can write it like this, N1 d by dt of phi. Similarly, in second coil, we will have EMF induced that is given by N2 d by dt of phi. Now here the flux phi is given by N1 I1, that is the MMF, divided by reluctance of the core R. And if we use this value of phi in this and in this equation, then we will get E1 equal to N1 is square divided by reluctance dI1 by dt, and E2 is nothing but N1 N2 divided by reluctance dI1 by dt. This can also be written as L1 dI1 by dt, and E2 can be written as L12 dI1 by dt. So from this we can say that L11 is nothing but N1 square divided by R, and L11 is called the self-inductance of coil 1. And similarly we can say L12 is equal to N1 N2 divided by R, which is nothing but the mutual inductance between coil 1 and 2. Now if we compare this and this, we can write self-inductance like L11 is equal to N1 phi divided by I1. That is nothing but flux linkage of coil 1 per unit current in coil 1. So self-inductance is defined as flux linkage of a particular coil per unit current of that particular coil. Similarly, if we compare this and this, we can say L12 is nothing but N2 phi divided by I1. That is flux linkage of coil 2 per unit current in 1. Here we are talking about flux linking a coil because of the current in another coil. After discussing the induced EMF magnitude, let us discuss the sign of the induced EMF. For this, we will use Lenz law. Lenz law says that the effect opposes the cause. The effect is the induced EMF and the cause is the flux, change in flux. Now the sign of E2 should be such that it opposes the change in the flux. The direction of E2 should be such that the current in winding 2 will cause flux in opposition of phi. So to get phi 2 in opposition of phi, the direction of current in winding 2 should be in this direction. If the circuit is closed, let's say we have a resistance connected at winding 2 like this. If we mark the terminals of winding 2 like this, A and B, then the induced EMF E2 will be between point A and B like this. And if the direction of current is like this, then the polarity of the voltage source should be minus here, plus here. Because inside the voltage source, the positive current goes from minus to plus, and outside the voltage source, it goes from plus to minus. In a similar fashion, we can find the direction of induced EMF in coil 1. So the direction of EMF induced in coil 1, E1, will also be like this. The direction of E1 in this way opposes the increase of I1 in this direction. That is why we can say the effect opposes the cause. If we have to mark the polarity of E1 in opposite direction like this, as shown by red, then it aids the flow of I1. It means it supports the cause. Therefore, the polarity given by red cannot be true, and the polarity given by blue should be the right polarity of induced EMF E1.